You know those big kinematic equations from physics class? The ones you probably spend hours memorizing? Well, what if I told you they aren't just random rules you have to cram into your brain? Turns out they have a secret origin story, and it all comes from the beautiful, elegant world of calculus. Today, we're going to uncover that story.
All right, let's dive in. To see where this all comes from, we got to go right back to the beginning. I mean, the very beginning. We're going to start with a fundamental question. What even is acceleration? So this right here, this is it. This is the definition of acceleration written in the language of calculus. It's basically saying that acceleration is just the rate of change of velocity over time. Super useful for telling us how things are speeding up or slowing down. But what if we want to go the other way?
And that's the million-dollar question, right? If you know how something is accelerating, like, gravity is pulling on an apple at a constant rate, can you actually predict its entire journey? Can you work backward to find out its velocity and exactly where it's going to be at any given moment?
Well, the answer is a resounding yes. And the tool that lets us do this, well, it's kind of the hero of our story today. It's called the integral. I love this analogy. Think of it like a rewind button for calculus. This process, integration, is basically the opposite of finding a derivative. You know how differentiation takes a function and tells you its rate of change? Well, integration takes that rate of change and gives you back the original function. It's awesome. So if acceleration is the change in velocity, then if we integrate acceleration, we should get velocity back. It's that simple.
Okay, so let's do it. When we integrate a constant acceleration a with respect to time t, we get this expression for velocity. But wait a second, look closely. It's not just a times t. There's this little extra piece that pops up out of nowhere, this plus c. That's called the constant of integration.
So what in the world is this c? Is it just some mathematical weirdness? Kinda. You see, the integral is great at finding the shape of the original function, but it has no idea where that function starts. That c could be any number, and it would just shift the whole graph up or down. But here's the cool part. In physics, c isn't just some random leftover. It actually means something real.
And figuring out what it means is surprisingly simple. We just have to ask, what was happening right at the start? Let's look at time t equals 0. Well, if t is 0, that whole at part of the equation just vanishes, right? And what are we left with? Velocity equals c. So c has to be the velocity at the very beginning. It's our initial velocity, or v initial. It's the starting condition of our journey.
And just like that, we've cracked the code. We know what c means. And now that we have this key, we can start building. We're ready to actually derive those famous equations of motion.
So let's do it. We take our integrated equation, we swap out that mysterious c for what we now know it is, the initial velocity, and voila! Take a look at that. Does it look familiar? It absolutely should. That is the first kinematic equation, and we didn't memorize it, we built it from the ground up, right from the definition of acceleration.
And here's the most important part. This isn't some magic trick. It's a recipe, a 4-step process. You start with a definition, you integrate, you use your initial conditions to figure out what c is, and then you assemble the final equation. That's it. So, let's follow that recipe again, shall we? This time, let's find an object's position.
Okay, round 2. We're using the exact same logic. We start with a definition. Velocity is the rate of change of position. So what do? We take that entire velocity equation we just built, the whole thing, and we hit the rewind button again. We integrate it to find position.
And when we run through those exact same steps, we integrate, a new c pops up, we look at time t equals 0 to solve for it, and I bet you can guess what it is. It's the initial position. And once we plug that in, we get this, the second major kinematic equation, the one that tells you exactly where something will be. Again, built, not memorized.
Okay, this is great. We've built this amazing toolkit from first principles. But this is all theory. Can these simple tools we've derived handle something messy? Something you'd actually see in a really tough physics problem? Let's find out.
Okay, brace yourself. Look at this monster of an equation. This formula gives you the range of a projectile on an inclined plane. This is a classic nightmare-level problem from exams like the JEE main. I mean, just looking at it is intimidating, right? So many variables, sines, cosines. Ugh.
Your first instinct might be, oh great, another giant formula I have to memorize. But here's the secret, and it's a beautiful one. This isn't a new rule. It's not new physics. It's just our simple 2-equation toolkit that we literally just built being used in a really clever way.
The way you tackle this isn't by memorizing that formula. No way. The trick is to literally change your point of view. You tilt your head, or rather your axes, to line up with the slope. Then you break everything down, gravity, initial velocity, into pieces that are parallel and perpendicular to that slope. And once you've done that, you just use the same simple kinematic equations we derived on each of those pieces. That horrifying formula? It's just the final result of doing all that algebra. It's not a rule, it's a conclusion.
So this brings up a really important question. Why would you ever go through all this trouble? I mean, why derive anything when you can just find a formula sheet and memorize it? And the answer, in one word, is adaptability.
When you just memorize, you only know what the equation is. But when you understand the derivation, you know why the equation is what it is. You understand why gravity suddenly seems to work differently on an inclined plane. You get why that magic 45-degree angle for maximum range doesn't work anymore. Memorization is fragile. Understanding is flexible.
I mean, let's just pause and think about what we did. We started with just two ideas, two simple definitions from calculus. That's it, just two. The idea that acceleration is the change in velocity, and velocity is the change in position. From those two seeds, we grew an entire toolkit powerful enough to solve everything from a simple falling object to that complex projectile problem.
And this is why this stuff really matters, way beyond the classroom. This way of thinking, of building from first principles, is the absolute heart of physics and engineering. It's how people design the curve of a highway, how they plot a course for a space probe, how they analyze an athlete's performance. The goal isn't to collect a bunch of formulas, it's to know how to build the exact tool you need for the job.
So, that leaves me with one last thought for you. We just saw how something as complex as motion can be completely unraveled if you just start from the very basics. And it really makes you wonder, doesn't it? What other big, scary, complicated ideas out there, maybe in economics or biology or anything else, are actually just simple rules in disguise, waiting for us to rewind them back to their source?